All right, let's get into it. Today, we're going to put on our detective hats and dive deep into the hidden world of Linux processes. Why? Because we're going to solve some of the most confusing mysteries you'll ever see in production.
So, let's start with a classic puzzle. You get an alert, the system load is absolutely through the roof. Users are complaining that everything is slow. But you pull up the CPU dashboard and it's just sitting there, practically idle. How is that even possible? This isn't just some textbook problem, this is a real-world thing that trips up even really sharp engineers. And today, we're going to crack this case wide open.
You know, you can think of your system like this huge, busy city. You've got thousands of processes all rushing around, trying to get their jobs done. And most of the time, it's a beautiful, organized chaos. But when a traffic jam hits, when our system grinds to a halt, we can't just look at the big picture. We've got to get on the ground, follow the clues, and really understand the secret life of all these processes.
Now, every good detective needs a toolkit, right? For us, that toolkit is the command line. These commands are basically our magnifying glass. They're how we interrogate the system and get to the truth. So let's open up the kit and see what we've got.
First suspect on the list, memory. It's almost always involved when a system starts feeling sluggish. But how do you find the real culprit? You see, a lot of the common metrics can be super misleading. So we need to ask the right question to get a straight answer.
And the key is this command right here. It sorts everything by RSS, which stands for resident set size. This is the crucial piece of evidence we're looking for because it tells us how much physical RAM, actual real memory, a process is occupying at this very moment.
In this distinction, it matters so much. VRT, or virtual memory, that's just the address space a process has asked for. It's like booking a giant warehouse, but then only using a tiny little corner of it. RSS, on the other hand, is the stuff that's actually in the warehouse. When you're running out of space, you don't care about the booking, you care about what's on the shelves. You care about RSS. It's a critical clue.
Okay, so another thing to remember is that processes aren't just lone wolves. They exist in relationships. They have parents, they spawn children, and to really understand what's happening, you have to be able to see their lineage, their whole family tree. This is how we trace problems back to their source.
And how do you see this family tree? Well, the -forest flag is going to be your best friend. It literally draws out the parent-child relationships, so you can see exactly which process spawned another. It's like having a map of all the system's families.
So let's really lock this mental model in our heads. Every single process is part of a tree. If you find some misbehaving child process just eating up all your resources, don't stop there. A good detective traces that problem up the tree to the parent. Because a lot of the time, the real bug isn't with the child, it's with the parent that created it but then failed to manage it properly.
All right, now that we have our tools, let's tackle our first case file. It's got a pretty dramatic name, but it's a classic system mystery, the rise of the zombie processes. So, what are they, and why should you even care?
So here's the difference. A living process is, alive. It's actively doing work. A zombie, though, is technically dead. It has exited, it uses absolutely zero CPU. The problem is, its parent process never came around to clean up the body, to reap it, so its entry just hangs around in the process table like a ghost in the machine.
So, how do we hunt for these ghosts? Easy. We can use our PS command and just filter for any process that's in the Z state. Think of it like a scanner for paranormal activity on your system. It'll show you any lingering zombies instantly. And here's the real deal. A few zombies here and there, totally harmless. But a whole horde of them? That is a massive red flag. It's a crystal clear signal that there's a bug in your application's code. Some parent process is not doing its job of cleaning up after its children. You see, you're not actually fighting zombies. You're fixing a broken family.
Okay, on to our second case, and this is the big one we started with. That totally baffling mystery of a system that's incredibly slow, but the CPU is just chilling. It feels like the system has hit some kind of invisible wall. Let's find it.
So this is the paradox, right? On one hand, system load is sky high. That means the system thinks it has a ton of work to do. But then you look at actual CPU usage, and it's super low. The workers are idle, but the line of tasks waiting to be done just keeps getting longer and longer. What is going on?
And this is the fundamental question our inner detective has to answer. The CPU is ready to go, it's willing to work, but something is holding everything up. All the processes are stuck. But stuck on what?
And here it is. Here's the culprit, the D state, also known as uninterruptible sleep. This means processes are waiting for something that they can't be pulled away from, usually really slow input/output, like trying to read from a failing disk or waiting forever for a network response. And the system load calculation includes these waiting processes, which is exactly why the load is high even when the CPU is free. And this is the piece of wisdom that separates a junior admin from a senior systems engineer. An idle CPU does not automatically mean a healthy system. It could actually mean a very, very sick system where everything is just blocked, waiting for I/O. Your detective work has to go way beyond just looking at the CPU.
So, we've solved our cases. But the job of a great detective isn't just about closing files. It's about understanding the patterns to prevent future crimes. So let's level up from just running commands to developing a real strategic mindset. This is basically a logical framework you can use for any performance problem. Instead of just guessing, you follow a clear path. First, can tasks even run? If not, why? Are they blocked like in our D-state case? If they are runnable, are too many of them fighting for resources at once? And finally, you check for memory pressure. It's a systematic investigation, not just random poking. And you can think of this as your detective's cheat sheet. When an outage hits, you just run down this list. For each part of the problem, CPU, memory, state, there's a core question to ask and a command to help you find the answer. It is a super fast and effective way to narrow down your suspects in the heat of the moment.
So, you've used your tools, you've found the processes in D-state, you rebooted that slow disk array, and the system is stable again. Are you done? No, not even close. The fire is out, but the real work, the true detective work, is just beginning. Now you have to ask why. Why did that disk start failing in the first place? Why wasn't it being monitored?
And this right here, this is the ultimate philosophy to live by. Fixing the immediate problem, that just gets the service back online. It's important, for sure, but true senior-level engineering is all about prevention. It's about doing the hard work of root cause analysis to make sure this specific fire never, ever happens again. You're not just a firefighter, you're a fire inspector.
So we'll leave you with this final thought. The next time you solve a big production issue, after the adrenaline is gone and everything's back to normal, just take a breath. Before you close that ticket, ask yourself, what's the one question I can ask right now that will lead me from the symptom to the true root cause and stop the next fire before it even starts? That's the secret life of a systems detective.